So let us start today with the equivalence of two system of forces. So what do we mean actually here? Is we have say suppose two system of forces. S1, S2. Here the forces are F1, F2. Suppose up to Fn, and here the forces are up to say F1 dashed, F2 dashed. Let me write below F1 dash, F2 dash, and up to say Fm dash. No, need not be of the same uh, cardinality. That means the number of forces may also differ. Doesn't matter. Okay. So here, these two system of forces are said to be equivalent if the effect of S1 on the body over which it is acting is the same as the effect of S2. Okay. So what do we mean by the effect? Then we are decoding it as like this. What we know whenever a system of forces act, what are the things we look upon? We look upon the resultant of the system of the all the forces acting. Resultant, say suppose of all the forces here, say R1 is for the source S1, a system S1, and R2 is for the system S2, and we look upon the sum of the moments of all the forces in the system. That means here all the forces, say if I say Mi is the moment of Fi with respect to any base point or with respect to any axis, the Mi, let me put a direction sign, then summation over Mi is the sum of all the force or sum of the moments of all the forces constituting the system S1. Similarly, let me say Mi dash as the moment of the Fi dash force. Okay, moment of Fi dash force with respect to the same base point. So what do we need? We need this summation over Mi. I want to, how many did I take? N equals to summation over Mi dash 1 up to M Mi dash. This should be equal. If these two systems are equivalent, then this should be equal, and also this R1 and R2 should be equal. That means if R1 R2 equal, then whenever we resolve it along any dimensions, here three dimensions we're considering, then the component wise also they should be the same. So these two conditions, this one and this equality, let me number it as 2. If 1 and 2 both hold, then I can say the effect of S1 will be the same as the effect of S2 on the rigid body, and that means S1 and S2 are equivalent in that case. So this is what we have written here. Okay. So now let us see whenever what are the tools we use to claim this equivalent, or rather whenever two systems are equivalent, then what can we use rather? Okay. So we have already used these things whenever we have done the coplanar forces. Actually, we will see we have used the first point and we have used the second point for coplanar forces. Now we are getting something extra here. What are the extra things? We will go on. First of all, what is the thing? If two systems are equivalent, or rather to bring it, we can treat a force as a sliding vector. We can treat a force as sliding vector means if you recall back, if this is the, say, suppose this is the point of application of the force F, okay, at the point A. But as you can see, the point A is lying on this line of support of the vector F, okay. Then I can easily slide this vector either in this direction, sorry. I can easily slide the vector in this direction or in this direction. That means the line of support remains the same. You can slide the vector along this line of support, either in this way or in that. That is the sliding of the vector. So if you want to produce equivalence of two systems of forces, then this is an allowed operation. I can slide the vector. Okay. Next is, suppose a couple is given in a plane. Let me first consider the case your couple is in this plane. That means the two forces are acting, and whatever movement, rotational movement it is trying to produce, you can as if think some screw is rotating either into the plane or out of the plane. So this is the plane of rotation. I can say that is the plane of the couple. So if this couple is given to you, I can consider the effect of the same couple. That means I can replace this couple by another couple lying in the same plane. That means I can say, suppose I can replace this couple by this couple. Okay. So this is also a valid operation here whenever we are considering equivalence of two systems of forces. Okay, this one. So these two are allowed up to coplanar forces. Now what else or what extra do we get whenever we consider forces in 3D? Suppose here, what did you do? We have replaced, or we can replace the other one couple C by another couple C dash lying in the same plane. Here what we can do, no need to lie in the same plane. You can replace the couple C in this plane, say P1, by another couple This is creating a problem. Let me write here. Okay. So this couple C, let me remove this one then. Hmm. If you have C in this plane, you are taking any other plane parallel to the original plane P1, where you are having the original couple C. You can replace this couple by another couple anywhere in the plane P2. That means what is the restriction we are putting? Key the plane P2 should be parallel to the original plane P1. So you can replace this couple by this couple. Okay. So this is also a valid operation here whenever we are trying to claim the equivalence of two system forces in 3D. Another last one, you can add up a finite number of couples by a single couple. That means you can replace the other. That is the last one, replacing several couples by a single couple. This one. Okay, the last point we are just saying here. Replacing several couples by a single couple. That means you have, say, suppose, let me take another larger one. You have this couple, you have this couple like this. You can ignore all of them, and ignore means you can replace all of them by another couple's C dash, such that C dash moment, if I say M, C dash moment, if I say M, or G rather, let me use G, it's better, G, then G will be having the same moment of all the couples we have replaced. Suppose I had N couples earlier times, so this should be the thing. I can replace all these single couples by this one. Okay, so these are all the valid operations whenever we are trying to just replace one system by another system. Okay, and we already know ki why do we do this equivalence of two systems. Suppose I have been provided with some system of forces which is very complicated to handle. Somehow, if I can replace that system of forces, or I can replace, or I can just substitute that system of forces by another equivalent system of forces, which is easier to deal with. I will deal with my whole analysis will go on with the easier system. So suppose you are given S1 system of forces, S1 system of forces, which is very complicated, and you are somehow replacing it by two S2 system of forces, which is easier to handle. So I will deal with the analysis of this. And as I say, these two are equivalent, then whatever analysis I do here is applicable here because they are having the same effect on the rigid body. So that is to our advantage of using this system instead of that one. And that is where we are taking the advantage of equivalence of two system of forces. Okay. Now, as I said, this the last tool which we have used for the equivalence of two system of forces. That means replacing several couples by a single couple. It is supported in the theory by this following theorem. Okay, what it is saying: the equivalent resultant of n couples of moments Gi is a couple of moment G, which is equal to nothing but the summation of Gi. As I said it. Now I prove it. Okay, this is indeed possible. Okay. The theory, otherwise, whatever I say, it doesn't make any sense here. So let us now prove this thing. Okay. So for that proof here, what we are doing, we are considering two couples actually, and you can extend it to any finite number of couples because the strategy remains the same. Okay. So for the simplicity, we are taking the most simple case. There are two couples. So G1 and G2. So first and foremost of all, let me just say here, there are two couples, G1 and G2. So for G1, I can think of as it is a couple I'm saying. So there are two forces, F1 and minus F1 acting at two different point of applications. And for G2, again there are two forces, say H1 minus H1. Again, they are the point of application are different. Minus H1. Actually, this is coming to the end. That's why it is shrinking off. H1 minus H1. Okay. So these two couples are given to you. Okay. Now, suppose M1 is a moment of this. As I said, G1 is the couple you are saying. So G1 is equals to, I can say, F1 into the distance separating between these two. So this thing. And for G2, for just I am considering, if you consider only the magnitude of the couple moment. So this one, again for G2, it is this one, right? And for G2, it is, let me write below then, H1T. So these two are given to you. So what we need to bring, I need to somehow add these two up, and that is replace these two separate couples by a single couple. Okay. Now what we do here, as you can see, instead of this couple, this H1 minus H1, I can do what? I can again replace it by another couple so that it has the same moment. Okay. It has the same moment. So that means what actually we are doing here, this is this reduction. The H1 can be replaced by another, that is G2 couple can be replaced by another couple having the same moment. I am using it for our own advantage. How we are using it? We are actually considering a straight line, say AB, right? And at the point A, we are suppose, let us consider our forces F1 and minus F1 were just acting at the point A and B respectively. F1 was acting at A, and let me just enlarge this figure. You can see it at a whole. This A1, this F1 is acting at A, and at B minus F1 is acting, right? And what we do, as I said, I can replace the couple H1, this G2 second couple, by a suitable couple. I do what I do the replacement in such a way that this couples is now replaced by F2. Let me call this D dash, then you can, it will better to handle D dash. So actually this will be or not D only, because you can easily understand these two are separate couples. So no need key, no, not necessarily they will be of the same distance. So D dash actually, but it will be now equals to D. So G2, this one is replaced by this one. How do we do? Because of the second tool we have considered here, this one. The second tool, or you can say third tool also, because you can take it in the say in the plane parallel to it. Okay, so either B or C. Okay, so via that, as it is a valid operation, we can make this replacement without violating any theoretical assumption. So for that thing, we are just putting at the point A. So what I started with, I started with A, where this F was acting, F1 was acting, and B, where minus F1 was acting. This is initially, D is the distance, perpendicular distance between the two. That's what is giving you this one, G1 equals to, okay. So now I do what? I replace this one. This might have been at some place like this and this H thing, H1 minus H1. What I am doing, I am replacing it. I am not considering this. Instead, I am considering these two forces suitably at this point, say F2 and minus F. Okay. So what is the requirement to be satisfied? The moment should be the same. So whatever the moment was, H1 D dash, H1 into D dash, it should be, that means it should be equal to now F2 D. Now you see, as this F minus F is fixed, so D is fixed. Okay. So what is the thing which could have, we have varied this F2 thing, there is the magnitude of the force. So we have incorporated whatever we need inside the magnitude of the force. So ultimately we are now not using this, but is using this F2D. So I have put F2 at the point A and minus F2 at the point B. So as soon as you put F1 and F2 here and F minus F1 and minus F2 here, by law of parallelogram of forces, I can add these two up. So get a resultant R1. Again, I can add these two up to get a resultant R. Okay. So let me rub all this out. So one thing that we mentioned, whenever they are doing it in the any of these textbook, they are not taking all this explanation. They are directly using you are putting F2 and minus F2. Now the question arises, can we really put it? Will the theory violate if I do like this? I just explained, the theory will not violate, because you are not at all violating the theory. You are using some of the tools for equivalent of two systems of forces, via which you can just put like that. Okay. So once I put like this, I get to this one. Okay. So what now we are doing? We have now, ultimately, let me just recall back what we ultimately have in our hand. We have two forces, G1 and G2, two system of couples, F1 minus F1 and F2 minus F2. Okay. These things all I have explained. So let the angle between F1 and F2 be this alpha. Angle between F1 and F2 is alpha. Now, if we are considering the angle between F1 and F2 as alpha, now let us use it. How we use it? G1 and G2. What are the G1 and G2? G1 is the moment of the couple, that is the couple itself. We are getting the moment of the couple. Now, what is the moment vector? Moment vector is always perpendicular to the plane constituting the forces. Okay. So G1 is perpendicular to F1. Likewise, G2 is perpendicular to F2, right? So what are the G1, G2 I have considered here? This is G1, this is G2. G1 is perpendicular to the plane of F1 and G2 is perpendicular to the plane of F2. Now, if alpha is the angle between F1 and F2, then the angle between the corresponding perpendiculars is also the same. So the angle between G1 and G2 here is also alpha. Angle between G1 and G2 in this figure is also alpha. Okay. Achha. Now, if these two forces are meeting at this point, then we can say again by parallelogram law of forces, we can add it up so as to get this G, the resultant. So I can write this resultant as G is equals to G1 plus G2. That's what we have written here. Now we will show somehow that this G is actually our required couple. That means what we try to do, we try to replace it, right, by a single couple. This G will play that. We just have to prove it. Okay. See, whatever we have been using with this F1 and this F2, this all will come inside this. We'll show how. Okay. So this thing, angle thing is clear right now. So G1, G2 perpendicular, angle between G1, G2 is also alpha. We have claimed it. Okay. So G1, G2 are vectors for convenience. Let us assume that G1, G2 are coordinating at some point C, as I have said. And R1, acha, one thing I mentioned, there is a typo here. Whenever I say R, I am meaning R1. Okay. Here, some places I missed this suffix. It will be R1 whenever I am, you can see the word R here. It is actually R1, not R. Okay. So there is some typo here. I cannot correct it right now. So I'm just mentioning it at the beginning only. Okay. So parallelogram forces, as I said, you can add this up. So resultant of F1 and F2 at acting at A is R1. And R2, similarly, resultant of minus F1 and minus F2 acting at B. If you can look at the figure again. As I said, this is the resultant. Here, see, I have written R. This is not R. This is R1 here. This is R1. This is R1. And this is your R2. This one, I have not shown it. Let me just show it here. This is at the B point, whatever you are getting. This point. This point, it is R2. Okay. So this R1 and R2. So R1 is between F1 and F2. R2 is between minus F1 and minus F2. So one thing is very clear. They are also becoming parallel. Let us see. Okay. So here R2 resultant of minus F1 and minus F2. Right? So R2 you can write like this. So ultimately what you are getting? Minus R1. So as I said, R1 and R2 are the same magnitude, but anti-parallel. That means opposite in direction. Line of support same, but the opposite in direction. So, okay. So what can I say? What is our main objective here? So R1, one force acting at A. Let me just draw it here. R1, one force acting at some point A, and R2, another force acting at some other point B. Point of application differs. Two forces you are getting of same magnitude but opposite direction, they definitely must constitute a couple. Okay. So what should be the moment of the couple? The distance separating them, perpendicular distance separating them. So perpendicular distance is D, so it should be R1 or R. Here it should be R1 again. So it should be R1 into D, moment of this couple. Which couple? Moment of the couple formed by the forces R1, R2. That means R1 minus R1 acting at the point A, acting at the point B. So this should be equals to R1 magnitude into perpendicular distance separating them, that is D. So R1 into D. Okay. Now let us come to the next second part of it. Second part means now the inclination part also we have to guarantee. What we are trying to prove? We are trying to prove that G will be your ultimate couple moment. G. You started with G1. You started with G1 and G2. You have been playing with all this R1, R2, you are originating from this G1, G2. Ultimately, I have to prove that this G1, G2 can be replaced by this G. So they have to prove the moment, the magnitude of the moment and the inclination also should be the same. That should match with this one. Okay, that is our main objective. So we have to ensure about the inclination part also. Here we are ensuring about the magnitude. The magnitude, you see, magnitude we are getting. This G is having this magnitude. We will prove that this. Till now, we have not proved that this is actually the magnitude of G1 plus G2. Till now, we have not proved that this is the magnitude of mod G1 plus mod G2. I have not proved it, but I will prove it shortly. So I will prove one thing. I will prove this magnitude same. G1 plus G2 I will prove. And also I will prove the inclination same. Inclination. That means its orientation is also same. Inclination of G equals to that given by the G1 and G2. Okay. So for that thing, what we do? I first of all, let me rub this all out. I first of all take theta as the angle between R1, again R not R but R1 as I say the typo here. It will be R1 and F. So theta will be the angle between minus R1 and minus F1 also. So what will be the R1's magnitude? Let me just go back to the figure if you have forgotten it or not recalling it. This is it. This is the theta angle between R1 and F. Okay, if you take the angle between R1 and F1 like this, then what will be the angle between R2 and minus F2? This will be again this theta only because F1 is a parallel to minus F1 and R1 is parallel to minus R1 that is R2. So the angle between these two will be also the same. Okay, alternate angle things or the correspondence angle, whatever you will just use the parallelity of the two lines, you will get the two angles to be same. Okay, so that's what we are using right now. So I am calculating, as I said, to prove, I will be proving the magnitude wise same, inclination also same. So first I am considering the magnitude. So R1 I am considering here the magnitude. How do we calculate the resultant magnitude? F1 square plus F2 square plus twice F1 F2 cos alpha. This is a simple thing we usually do for the vector addition. So this thing, as I said, I will be proving the magnitude same for G equals to G1, G2. That means this portion I will show, this one, G1, G2 magnitude wise same, and also the inclination portion will be same. Okay. So I am using this theta, angle between minus R1, R1 and F1. Similarly, angle between minus R1 and minus F1 also the same because R1, what is minus R1? Minus R1 is parallel to R1. F1 parallel to minus F1. So if the angle between these two lines is theta, then definitely corresponding, if you take the parallel lines, the angle will remain the same. So now R1 magnitude is given by this thing because alpha is the angle between these two F1, F2, and tan theta will be given by what? F2 sine alpha by F1 plus F2 cos alpha using this figure. F2 sine alpha by F1 plus F2 cos alpha. These two are known things you can recap back from any vector theory class. Okay. So once you are doing this, let me just see how it will help us to bring or rather prove it. Okay. Now, if you construct a parallelogram with G1 and G2 as adjacent sides, what will be the length of the diagonal if you are constructing a parallelogram with G1 and G2 as the two adjacent sides? Okay. Let me just move it here. You are constructing a parallelogram with G1 and G2 as two adjacent sides. You are considering like this. Okay, it's just a bit of inappropriate drawing, whatever. G2. If it is it, then the parallelogram distance length, a diagonal of the length of the diagonal for this parallelogram is given by this thing, G1 square plus G2 square plus twice G1, G2, angle in between the two. So what is the angle in between the two? This is theta. Sorry, alpha. Okay, so cos alpha thing. Okay, the G1, G2 is this thing. So if you put it, now what was G1? Recall back, it was this thing. G1 equals to F1 into D. So G1 was F1 magnitude into D. So that's what we have used. Similarly, that's what from G2 we are getting. Okay. And similarly here, so ultimately, if you just simplify it, you are going to get, this is again R1, not R, my mistake. This is R1. So this is G. So you started finding out the length of the diagonal of this parallelogram, having the adjacent sides G1, G2, you ended up finding G. So the length of the diagonal is not G, right? And also the diagonal is inclined. As I said, here I have to take care of the inclination also. So the diagonal is inclined to G1 at angle alpha. What is the angle alpha? At some angle, what is the angle? So suppose I name it as inclined at G1. So this is the figure, right? Let me just shift it. So this is the figure here, this one. So there's the, let's say beta. Okay. So I'm trying to find out tan beta. So beta equals to something S here. So tan beta is what? Whatever the angle you are having between G1, G2, it will be used here. So it will be G2. If it is the angle G1, G2, in between these two, it is angle alpha, as I said before, because the angle between F1, F2 was alpha. So it will be G2 sine alpha by mod of, obviously mod of, by mod of G1 plus G2 cos alpha, right? But what is G2 again? Again F1, G, G2, sorry, G1 F1D and G2 F2D. So whatever these things we have, we are just putting it here. So DD cancels out. Ultimately, you will get this thing, this. But what is this thing? This is nothing but theta. See, we have Before beginning this, we have already calculated it here, tan theta. So the angle tan beta is equal to tan theta you are getting. Tan beta we started with. Okay. So you are getting here is equals to tan theta. Here, tan theta. So theta equals to, you are getting this thing. So angle in between G and the G1 is equals to the angle between F1 and the resultant R1. Okay. So this proves the inclination is also the same. That means I am ultimately having two vectors, G1 and G2, and G turns out to be the resultant of these two. And G's value turns out to be this RD, that is the resultant, whatever we started with this thing, R1D, R1D, that means here, R1D. Now what is R1? R1 again we have calculated it as we see this is for there. That is now at above this thing R1. So you can simply plug it in here, this formula. So I'll be getting here. So G is equals to, let me just shift in this direction. G is equals to, I can write root over of F1 square plus F2 square plus mod of F1, F2 into cos alpha. So see, everything we had in terms of the two couples formed by the forces F1 minus F1, F2 minus F2, we are able to bring it here in G's moment to D, whatever D you are having here, resultant of this into D. Okay, and the angle is also the same, this theta angle. That is the angle between F1 minus F1, whatever the angles were there, it is now shifted to the angle between G. So whatever the two couples were produced by F1 minus F1 and F2 minus F2, now you can think or replace it by another couple, G single couple G. There were two couples here, C1 and C2, or G1 and G2. Now you are replacing it by a single couple, and that is possible. We proved here. Okay. So this concludes that about the diagonal proof that G is represented by the diagonal of the parallelogram with in both magnitude and direction. So we are supposed to find out the resultant of the two couples. We have find it out. So by definition of sum of the two V vectors, V is equals to G1 plus G2. So in general, I have proved with the two couples, you can just generalize it to n couples. Okay. And likewise, once you have got this equality, the component-wise equality is just a trivial fact. So GI, if you just break like this, LI, MI, the DCS of any line of vector, the moment you are talking of the moment vector you are getting. So moment vector means you are getting a line in 3D. That means you are getting a line in 3D means it has this DCS, duration cosine. So I name it as LIMI. So G is equals to, if you are adding this up, so all this DCS should be adding up component wise, adding up will be there. So you are getting like this. So if you just take the resultant, you are going to get like this. And so the duration cosine ultimately just a normalization here, G, whatever magnitude you are getting. L by norm G, M by norm G, and N by norm G. So this is how we have proved the theorem. Okay. So let us stop here.